Have you ever wondered how your phone talks to the internet or how two different apps exchange information? That's where something called an API comes in. API stands for Application Programming Interface. But don't worry, it's not as scary as it sounds. Think of an API like a TV remote control. You point the remote at the TV and press a button, maybe volume up or channel down. You don't need to know how the TV processes the signal, how the circuits work, or how the screen updates. You just press a button, the remote sends a request, and the TV returns a result. That's exactly what an API does. The remote is the client sending a request. The TV is the server doing the work behind the scenes. And the button you pressed is like an API endpoint. APIs let one system communicate with another system in a simple, predictable way, just like a remote control talking to your TV. Now that you get the idea, let's look at the most popular web API, the REST API. REST stands for Representational State Transfer. A lot of people think REST is a protocol like HTTP or HTTPS, but REST isn't a protocol. REST is actually an architecture style. Basically a set of rules or guidelines that tell you how to build an API. Imagine you walk into a library and you want to find a book. Instead of talking to a librarian, you use a simple machine with buttons. Press one button to get details about one book, another button to add a new book, and another button to remove a book. The machine always works the same way, no matter what book you want or who is using it. A small, predictable set of actions you repeat on different resources. REST works in a similar way. Everything in REST is treated like a resource, just like each book is a resource in the library. And you interact with these resources using actions that are built on top of HTTP methods. So let's talk about those methods. They're basically the verbs of the internet. Get method is used to request or read data. For example, get the list of all users. Post method is used to create something new. For example, create a new user account. And put method is used to update an existing resource completely. Patch is used to partially update something. For example, update just the user's email instead of the whole profile. And delete method is used to delete a resource. Imagine a client, like a browser, a mobile app, or any front end, needing some data from the server. The client sends a request to a resource URL. The request travels to the server. The server handles the request, reading from a database, running logic, or validating input, and then sends a structured response back. Now that we know how REST works, let's look at what makes it unique behind the scenes. REST is stateless. The server doesn't remember anything about previous requests. Every request must include all the information needed, just like asking a librarian something and having to reintroduce yourself every single time. That's how REST stays clean and predictable. REST is platform independent. It doesn't matter if the client is a mobile app, a website, or even a smartwatch. If it can send an HTTP request, it can communicate with a REST API. REST is flexible. It's not locked into one specific data format. Most modern APIs use JSON, but you can just as easily return HTML, XML, or any other format the client understands. And it's easily cacheable because REST works on top of standard HTTP. It benefits from built-in browser and server caching. REST is used pretty much everywhere because it's simple and universal. Some common examples include public APIs, mobile apps, social media APIs like Instagram, and e-commerce websites. REST is great, but it's not always the best choice. It can struggle with fetching complex and deeply related data in a single request, or handling highly complex data relationships, real-time updates, or constantly changing data, and situations that require many back-and-forth requests. Now let's move to a modern, high-performance API technology that's becoming very popular in microservices and back-end-to-back-end communication, gRPC. Before we understand gRPC, we need to understand RPC, or Remote Procedure Call, and how it differs from a local procedure or function call. A local procedure call is just your program calling a function inside the same process. Everything happens in memory, it's fast, and nothing crosses the network. A remote procedure call takes that same idea, but the code you're calling is on another machine. So instead of a simple in-memory function call, the request has to travel over the network, executed there, and then the result comes back. RPC has been around a long time. Older versions worked well for their time, but they had some limitations. They were dependent on text-based payloads, which are slower and larger, and they were not optimized for modern high-traffic systems. And that's where gRPC comes in. gRPC is Google's modern take on RPC, designed for speed and efficiency. gRPC, instead of using JSON or XML, uses protocol buffers, also known as protobuf. So why not JSON? Why protobuf? JSON is human readable, which is great, but machines don't need readable text. They need fast and compact data. Protobuf is a binary format, which means much smaller message sizes, much faster serialization, strong typing, and defined contracts between services. With protobuf, you define your data structures and service methods in a .proto file, and gRPC generates the code automatically for different languages. Protobuf is simply a way to take a data object, convert it into a tiny binary format, send it over the network, and then rebuild the same object on the other side. It's fast, compact, and ensures both the client and server speak the exact same data structure. gRPC uses protobuf under the hood, but adds the whole communication system around it. When your app calls a function, gRPC automatically turns that call into a protobuf encoded request and sends it over a fast HTTP2 connection. On the server side, gRPC receives the request, decodes it, runs the actual function in your backend, and then sends the response back using the same protobuf process. Because all of this is generated from your .proto files, you don't write any networking code. gRPC handles serialization, routing, and communication for you. The result is that calling a remote service feels just like calling a normal function, but with high performance, low latency, and built-in support for streaming in both directions. gRPC runs on top of HTTP2 instead of HTTP 1.1, and that alone gives it a huge performance boost. With HTTP 1.1, each request basically needs its own connection, and they often get stuck waiting for each other. That's where delays and bottlenecks happen. But HTTP 2 fixes all of this. It lets multiple requests travel over a single connection at the same time, without blocking each other. Every request becomes its own independent stream, so even if one is slow, the others keep moving. This multiplexing dramatically reduces latency, removes head-of-line blocking, and makes gRPC perfect for high-speed, real-time communication. That's why gRPC feels so fast. Because gRPC is built on top of HTTP2 and uses protobuf for its data format, you end up getting a bunch of performance benefits automatically. You get more speed because protobuf messages are tiny and HTTP2 can send multiple requests at the same time. You get lower CPU usage because binary serialization is much cheaper than dealing with JSON. You get lower latency since requests don't block each other the way they do in HTTP 1.1. And you use less bandwidth because protobuf payloads are far smaller than traditional REST responses. All of these pieces fit together, and that's what makes gRPC one of the fastest communication systems you can use today. We just talked about why gRPC is so fast and efficient, but speed isn't everything. So let's talk about where not to use it. gRPC is not a good choice for public APIs because most developers expect human-readable JSON. It also doesn't run natively in browsers without extra tooling, and its binary format makes debugging harder in systems that rely on readability. But inside your backend, gRPC absolutely shines. It's ideal for internal microservices written in different languages, all communicating through super fast gRPC calls. With an API gateway at the edge, you can expose REST API externally while keeping high-performance gRPC inside your system. Now let's talk about another API style that came long before REST and is still used in mission-critical systems, SOAP API. SOAP stands for Simple Object Access Protocol, although ironically, it's not that simple. Unlike REST, SOAP is actual protocol, with strict rules about how requests and responses must be formatted. Think of SOAP like sending a formal business letter. You must follow a specific structure: the header, the body, the signature, everything in its place. If anything is out of order, the letter might be rejected. SOAP works in the same way. Every message is wrapped inside an XML document with a fixed format. In SOAP API, the client and the server don't talk to each other freely. Everything has to pass through a strict layer of SOAP standards. This layer defines exactly how messages must be formatted, how errors should look, how security works, and even how the data itself is wrapped. So instead of sending raw data directly, SOAP forces both sides to follow a predefined rules. To understand SOAP better, let's break down the main parts of a typical SOAP message. Envelope is the outer wrapper that defines it as a SOAP message. Header is extra information like authentication or transaction IDs, and body is the actual data or operation being requested. SOAP messages are always in XML, which makes them very structured, but also more verbose. One of SOAP's strengths is that it doesn't depend on just one protocol. SOAP can work with HTTP, HTTPS, SMTP, and TCP. This flexibility is part of why SOAP is used in environments where reliability matters more than simplicity. SOAP is extremely formal when it comes to defining how systems talk to each other. It uses something called WSDL, Web Services Description Language. WSDL is like a detailed contract between two systems. It describes what operations are available, what data types are allowed, what structure every message must follow, and how the service should be contacted. This contract-first approach reduces misunderstandings between systems, especially in large organizations. Even though REST is more popular today, many large institutions still rely on SOAP because they need predictable, tightly controlled data exchange. And their old systems were built with SOAP and are still reliable today. In these fields, stability and rules matter more than flexibility. So how does SOAP compare to REST? SOAP always uses XML. REST uses JSON or XML. SOAP is strict and structured. REST is flexible and easy to use. SOAP has built-in standards for security and transactions, while REST relies more on external tools. SOAP is better for enterprise-level integrations and legacy systems, while REST is great for web and mobile apps and public APIs. Now let's talk about GraphQL, modern API technology that gives clients more control over the data they receive. GraphQL is a query language for APIs, but not a database query language. A way for client apps to ask servers for exactly the data they need, in the exact shape they need it. Instead of calling multiple REST endpoints and combining responses together, GraphQL lets the client make one structured request and receive one predictable, nested response. Facebook created GraphQL when their mobile apps started dealing with a massive web of connected data, users, posts, comments, reactions, and replies, all tied to each other. Traditional REST calls kept overfetching and underfetching, forcing the app to make several round trips just to render a single screen. So Facebook designed a new approach, a query language that could walk this entire graph of relationships in one request. When a client wants user data in a typical REST API, it often has to call multiple endpoints. One request for the user, another for their posts, another for comments, and maybe even another for likes. This is called underfetching. The server gives you only part of what you need, forcing the client to make several round trips just to build one screen. GraphQL solves this entirely differently. Instead of chasing each resource through separate endpoints, the client sends a single query to one GraphQL endpoint and asks for the exact shape of data it needs. The user, their posts, their comments, all nested inside one request. The server then returns one complete, structured response. No underfetching, no extra requests, just the data you asked for. In REST API, even for a simple need like getting only the first name of a user, client still has to call a fixed endpoint that returns the entire user object. This means the client receives way more data than it actually asks for, a problem known as overfetching. GraphQL solves this by letting the client send one flexible query to a single endpoint and specify exactly which fields it wants. So instead of receiving the whole user record, the client gets only the fields it requested. This gives the front end full control over the shape of the data, eliminates overfetching, and makes communication between client and server much more efficient. GraphQL is built on three core components: the schema, the operations, and the resolvers. These three pieces work together to define what your API looks like, what clients can ask for, and how the server actually returns the data. Everything starts with the schema. The schema describes the entire shape of your API, what types exist, what fields they expose, and which operations clients are allowed to run. It's the contract between front-end and back-end, and clients can only query what the schema defines. Once the schema is in place, clients interact with it through operations. Queries are used to fetch data, mutations handle create, update, and delete actions, and subscriptions deliver real-time updates. Every request a client makes is simply one of these operations, asking the server for exactly the fields it needs. And finally, resolvers. Resolvers are the actual logic behind each operation. pulling data from a database, calling external services, or performing any custom computation. They can be written in any language, and they are the engine that turns a client's operation into real results. Now that we understand the three core parts of GraphQL, let's talk about when GraphQL is actually the right choice. GraphQL really shines when your data is highly nested or interconnected. If your client needs a lot of flexibility in the shape of the response, GraphQL gives you that control. It also provides strong typing and automatic self-documentation straight from the schema, and it's a great fit when multiple clients, like web and mobile, are consuming the same API but need different slices of the same data. But like any technology, GraphQL comes with trade-offs. Caching is one of the biggest challenges. With REST, each resource has its own URL, so browsers and CDNs can cache responses easily. But GraphQL sends everything through a single endpoint, usually /GraphQL, and the response depends entirely on the query body. That means two requests to the same endpoint might return completely different shapes of data, which makes traditional URL-based caching almost useless. On top of that, GraphQL usually comes with a heavier setup and more tooling compared to a simple REST API. There's additional complexity and overhead, especially if your schema is not modeled carefully. And because clients can request any shape of data, it introduces security challenges as well, making authorization, monitoring, and rate limiting harder to manage. And this brings us to the end of part 1. We've covered REST, gRPC, SOAP, and GraphQL, the foundations. In the next part, we're diving into the real-time and event-driven side, WebSockets, webhooks, server-sent events, and also WebRTC,